Perfect. Go ahead.
Awesome. So I'm presenting this paper, Acquiring Diverse Skills Using Curriculum Reinforcement Learning with Mixture of Experts. Here's the authors. Let me get a laser pointer. Yeah, here's the authors. So going to go through the background. It's SEPs. I'll describe what that is. Energy-based curriculum model, and they have to find tractable lower bound optimizations and show you some of the results. So let's dive in. So contextual episodic policy search SEPs, it doesn't rely on the Markov assumption. So it takes in contexts instead of states. You can think of these, so this is for, you take in a specific context for an entire episode, then you might sample new context for the next episode, and we'll get into the algorithm a little later, but you can, in these motion primitive robotics tasks, you can think of these contexts as like the desired strike location of a tennis ball, or placing a box on a table, the position you want to place it. But while it's not discussed in this paper, it can be extended to non-motion primitive sort of things too. So we explore via maximum entropy. So we have, and I'll get into these distributions in a sec, but for some episode, you define a reward and you have some entropy term that rewards for exploration. So note that there's no automatic curriculum adjustment here. So curriculum adjustment is when the context changes automatically to get more and more difficult as the agent learns. And our expectation here is over the actual context space. And I'll talk about why that is, or what we're going to do about that in a sec, because this is often not known, the context of your environment.
So just to understand all of the notation, sorry,
Go ahead. Yeah, totally.
Really slow. So C is your context, right?
Yep. C is the context.
Now,
it's
theta are the trainable parameters.
No, so theta is a motion primitive. So that is not an action. It is a trajectory. For in this paper, like robotics, it is a motion primitive. So it's a trajectory. It's it might be a parameterized.
Sure. It's a state of the. Okay, so it's a future trajectory or a past trajectory?
The optimal distribution.
The future, the one that you're trying to get.
Yeah, okay. Exactly. And in this case, it actually spits out a Gaussian distribution of motion primitives of trajectories. Sure. So, and then you sample that and pick the best one.
Now, if you want. R, what is capital R then?
R is a reward. So
reward. So given some context and given some trajectory, it tells you what the reward is.
Did you? So for example, you'll see there's a robotic arm that's trying to move a box and place it to a specific location in the table. So the context in this case would be the location, the goal location that you want the box to be placed. Theta would be the motion primitive, the trajectory to get there. R would be whatever reward the modeler assigns to getting there.
Sure.
And then obviously H is the entropy term. And so this
what is pi? What is pi here?
Yeah, so pi is the search distribution. So that's what you're looking for. That is the policy. So input a context, get out a motion primitive, and give it to your motors in your robotic arm or your trading algorithm or whatever you're trying to do, right? So that is the goal. Pi theta c is the goal. That's what we're looking for. Yeah, that's what we're learning, right? Does that make sense? Okay, so so then we add some KL regularization here. So this is so I'll go over in a second. So pi theta c, we can use, we can expand this, and I'll show you how that's expanded in a second, to get pi c. So this is the context distribution. So this is our learned distribution of context. So remember I said the actual context space is here, is P of C, and that often isn't known. The robot doesn't know the whole space of the table that it's trying to put a box on, right? And it might even have places where it can't go, like if you picture yourself trying to scratch your wrist with the hand that it's connected to, you can't actually reach your wrist, right? So there's contexts that are off limits, and the robot doesn't know that. So we learn these, and I'll show you how we learn those, but we want to KL regularize that. So make sure it doesn't change too drastically, this learning from the actuals. So we'll sample this actual context space using the environment and see how much pi c deviates from that using KL regularization. And so if you look at the definition of KL regularization, it's an integral over a log ratio of these two. We're taking the max of a negative, so we're actually minimizing KL. So this is an I projection. If stop me if you all know this, but so where this mass, so basically this is mode seeking. So where PC has a lot of probability mass, so will pi c. And where it doesn't, it won't, right? So it's mode seeking. So it finds the peaks of pi c. And this is good for mixture of experts because our goal for the experts is to find specialized diverse skills of each expert. And I'll show you this in a second. And so this is one way it does that. So this context is learned.
Jacob, one more question.
Automatic.
So E is,
yeah, go ahead.
Yeah. So E is the expectation value, right? Or what is E?
Correct. Mm-hmm. Yeah, E is an expectation
both
value.
Inside the bracket.
Yep. Mm-hmm. Yeah, and so that's saying, so this is saying, so there's no pi c dependency here. Well, I mean, pi theta c depends on pi c, and I'll show you that in a second. But this is the basic regulars optimization term, optimization problem. So we want to maximize reward and we want to maximize exploration with given some alpha. And then we want to do that over a typical context, an expectation value of context, right? So expectation value.
You want to maximize the expected reward.
Correct. Yeah.
With the expected, context.
Based on an expected context. But now we're doing that based on a learned context, an expected learned context.
Sure.
And we're regularizing that. Yeah. So, and we're maximizing both. So this is, I'll show you, this is going to become intractable. And we're going to approximate this with two separate optimizations for each of these. So this is our distribution. So it's a gating. So this is the gating distribution. So this is how you choose an expert. So take a higher level view in case people aren't familiar with mixture experts. Instead of training one giant model of one huge network with a ton of nodes, we have a bunch of smaller networks, and each of these learns a specific task or a specialized skill set that helps. So you might think of tennis, the context might be a specific point you want the ball to go on the other side of the net. And you can say, you can backhand it, you can, I don't know tennis, but you can do all different types of strokes to hit the ball, right? And each expert sort of learns their own stroke. And there's actually, that's shown in the results of this. But in order to do this, you have to learn which expert is best for the context you've sampled, the input context. You need to learn which expert is going to handle that context the best. And that's the gating distribution that does that. And that's this. Over here is what we're now learning. So now it just has an O, whereas previously, it's just theta C. But theta C, it depends on O because we have to pick an expert. There's multiple experts that can give you the output, right?
So O is a parameterization for experts?
Correct. It's the index.
For outputs.
It's the index of experts. So if you have 15
an index for experts. Okay.
Yeah, if you have 15 experts, this is a sum over 15.
15.
Right?
Okay.
Yeah, exactly. K experts, whatever.
And do you demand this to be normalized to 1 here?
Yeah, it would be normalized 1. Typically, so you would choose, so using Bayes' rule, you can expand this to this ratio and it sort of decouples pi c and pi o. So pi o you can think of as the baseline distribution of picking an expert. So like what probability do I have to pick expert 7 for this given context? And typically you just set that to an equal probability, and you can update that in the learning if you want. In this paper, it was kept constant over training, but and then pi c is the probability of a given context. Remember, that's we'll see, we're learning this. That's how we update curriculum. And pi co is given an expert, what's the, what context does that expert want to focus on, right?
Sure, but this whole ratio is just nothing but PO given C, right?
Yeah, exactly. Yeah,
So
and
this
so I have,
so if it is probabilities, then of course once you add over O, it should give
mhm,
you one.
yep,
But
absolutely.
again, you
No,
keep
totally.
calling it policy, not probabilities. That's why, I mean, are you using
Oh,
these two
so
things interchangeably?
it's a distribution. Yeah,
Yeah.
policy distribution. I'm
Okay.
using
That's
interchangeably.
fine.
Yeah,
That's
yeah,
fine.
yeah. So I think of a policy as like, it's a distribution, but it's the policy that tells you, like, this is, given a context, this is your best pick for your motion
Yeah, but
primitives,
no,
right?
but then two is just nothing but the definition of probabilities
Yeah,
here.
no, totally, absolutely,
Yeah, so
absolutely.
there's
Yeah.
if they are probabilities, yeah.
Hmm. Yep. So this can be expanded, and if you want to derive the expansion, you can go to this reference in the paper. But this is intractable because there's summations in these logarithms, and theta c depends on CO, as we saw with the gating probability. So this becomes intractable, and so we come up with these lower bounds. The paper comes up with these lower bounds, and this is also in Celic here. That reference, they actually derive it in this paper. So this is nothing new here yet, and I'll show you what's novel about this paper. But
What do you call by expanding? Are you expanding like Taylor series expansion? Is there a small parameter, or you
uh,
expanding definitions?
I didn't dive too deep into this reference,
Okay, okay.
but yeah, I'm pretty sure they're just actually plugging in
Like what is alpha, what is beta?
this instead of just keeping. Oh yeah,
No, no,
so
there are some parameters there, alpha, beta,
yeah,
that were
yeah,
not
those
there
are
before.
hyperparameters, right? To tell you how much you want to value a given expert, and how much you want to explore, and everything. And this will get simpler. If you want
Okay,
this derivation, I
sure.
encourage you to go to that citation.
Maybe
Uh,
there's some model for the probability distributions that they use, and in those models there are alphas and betas
oh yeah,
appearing.
yeah, and just like any model, these are hyperparameters to decide how much you want to value. And in the results that I'll show you, they actually do ablation studies where they start taking away these hyperparameters to show you that you do need these terms. And um, so they come up with these tractable lower bounds. Excuse me.
Okay.
Um, so they come up with these optimizations, tractable lower bounds, that are essentially a surrogate. They're a conservative estimate for that super big, intractable single optimization. And now you notice we're optimizing first the actual, so first we optimize the actual context distribution for the expert. This is a per expert context distribution. This is the context that that expert prefers, right? We're optimizing for that. And then using that, we can optimize the actual policy for that expert. And I can show you this algorithm, but they're making this tractable by using an approximation that is the last episode's policy and distribution, and that these expand to this. And so what this does is, so I have some highlights. So this is specialization. So if you think about pi old, this is, so pi old, this is the last episode's distribution. So if there's a context space that episode had a high probability of solving, we're rewarding that here, right? And similarly, if there was this is the context space, this is the motion primitive. So we're rewarding specialization here because this context space is preferred by that when this is one, right? This is yeah, this is we if this is one, we're rewarding that, right? If this is zero, this is negative infinity. So
Okay, so
if this
is the
if
idea
the
then sorry, so is the
yeah
idea then to have for each context to have one and only one expert? Is that like have fewer experts
for
for a given context? Is that
each there's a figure later that shows this, but it's a context space for each expert. Yeah. So there's a whole context space, right? That is everything in the universe for that problem. And then each expert specializes and it has a subset of that space.
no,
Um,
I understand, but then here you maximize some property subject to the pi. You're
mhm.
maximizing this some quantity for all possible distributions, which are pi c given o. All right. So this is what this expression means, equation number
Yeah.
five. Yes.
Uh-huh. Yeah.
So then you are trying to maximize whatever
It's
property you have there.
it's actually pi o given c. So
No, but it's not that's not what's written on the under maximization.
well, I mean, Bayes' rule, you can make it the other way with the ratio, right? So
Well,
um,
but what is it that you're maximizing? That's what is
yeah,
it that you're varying? Because pi tilde, as I understood, is what's the difference between pi tilde and pi? Pi
the
tilde is
last
old one. Okay.
the last episode.
Okay,
So
so
that's
then you're not changing it. That last episode, it's
correct. It's calculable.
yeah.
You learned it. That's what you cranked out on the last training episode, right? And so you have that. It's calculated, but
Mhm.
it's a probability that this expert liked that context space, right? So it's
But then it's
specialization.
just a number. Then it's just a
Sure.
number. So like,
I mean, it's a distribution, but yeah, it's yeah,
well, fine. It's a distribution, but okay. So and given this distribution, you want to find the other distribution which maximizes this uh, of expression number five. I think that's the
yeah.
idea.
So yeah, exactly. So if the expert has a high probability of choosing that context space, you reward that, right? If it has a low probability, you're rewarding it less,
Well,
right?
I guess that's what I don't see because in equation five, I do see that the third term depends on pi, c given o, and I
Yeah. So
understand.
I'm about to describe that over here. So
But the second term doesn't depend on pi c given o. It depends on the pi tilde o
mhm,
given c or pi tilde c given o. So it depends on the previous things,
yep.
not so
Yeah.
you're not going to be changing this term if you change your pi c given o.
Correct, but that's a direct measurement of how well your model fit that
Yes,
space. So
yes, yes.
so you continue to fit that space if it fit well, and you de-incentivize it if it didn't fit well, right? With the log. That's what the
Yeah,
log is doing. And then you choose some hyperparameter. These are all variable, and you choose this to decide how much you want to reward. And that's the art
sure.
of this, right? So then you use entropy for the current run to explore, right? This brings diversity in the current run
Mhm.
because so you have specialization on the last iteration, diversity for the present iteration. This
Mhm.
incentivizes each expert to fully explore its space. So like you're fighting, these fight each other, right? Like you're trying to explore, but you're also trying to specialize. So you have to pick beta and alpha. I'm sure there's a huge art to this. I've never actually implemented this, but I'm sure this can be difficult to decide how to choose beta and alpha, right?
No, that's just hyperparameters, right? So they're not
Yeah, yeah, totally.
not
But
so I mean maybe some place inside of this pi tilde secretly pi is hiding and then maybe when
oh,
you look
There
at
is
the whole
expectation value actually in the first term. I mean, in the equation 5, you mean, Vitaly. Do you see
yeah,
expectation value? It's depend on pi.
right, but if you add a constant to this thing if pi so if
Oh
pi
yeah, I
tilde
see, I
depends
see,
on
I see, I
pi
see. maybe.
then yeah. But if pi tilde doesn't depend on pi, it's just non-existent for this variational principle.
So yeah, and I think I have a slide that'll help with that
Okay.
in a sec. So this is where, so everything I've described so far has been done before. This paper is the novel part of this paper is, so everything before has used Gaussian context distributions. And Gaussians are continuous, and they don't necessarily, for each mixture of expert, the context space is classified as a Gaussian sampling. And this uses what I'll show you as an energy-based model. And the authors claim, this finds discontinuities better. And this is what I was talking about. So if this is a table where you can place an object, a robotic arm can place an object, then this might be the robotic arm trying to scratch its wrist, right? And it can't do it, or some other off-limit space. There might be an object here that it can't, has to go around or something, and this is the edge of the table. And so they claim that the nonlinear energy function that we're going to see in a sec helps find these discontinuities and edge of the table better, and it doesn't waste compute on learning these invalid contexts. So here's the energy. So this is actually CO, pi CO. So it's an exponent over Z. So here's, we've talked about a lot of distributions. I've put them all on a table here. So, so this is the actual context space. It's usually unknowable, P of C. Pi theta C, that's what we're trying to get. It has a gating policy with the expert's actual motion primitive distribution given a context. What motion primitive do I want to carry out? That's what we're trying to find. Pi OC, this is the gating distribution given a context. Outputs the probability of choosing expert O given context C, right? So this is the per expert learned network. So you can see that's how we're learning the actual policy. So this is a neural network for each expert. This is the energy function. We're also learning this, but we're learning it through the, so this is actually, sorry, this is the context distribution that assigns an energy to each context. So energy being how valuable, it scores each context, right? For that expert. For expert O, it gives this context a score. Is it good, is it bad? And this is learned, right? This is a neural network. Phi C is a neural network. And so Z, I'll show you, that's an approximation. This, if this should be an integral over all context space, but that's intractable. So it's an approximation. I'll show you that in a sec. So we're learning with a neural network, phi of C. This is pi C. This is the learned distribution. And again, we're learning this through pi CO, which is learned through phi C, which allows us to learn our entire context distribution.
Well, the only thing here is learned is phi OC.
Yeah,
the
right,
rest is just calculated.
But these all depend on, yeah, exactly. Yeah, these all depend on phi C. So
yeah.
So pi O, that's the baseline. Again, it usually starts uniform. It can be updated. It's not updated in this paper. And these are the pi olds. They use it to make the optimizations tractable. And yeah, so we can come back to this. So what's new about this paper is specifically these distributions.
But
so
sorry,
yeah.
I mean, since it's new, we maybe should actually talk about this. So
yeah.
So here, writing some function phi O of C in this way is not,
Sure.
It's straight. I mean, you can always take any phi O C and write it this way. So I guess the question is how to learn. Okay, energy, you call it energy of a given expert for a given context. So how to learn that? So that's maybe
Yeah, and hopefully I do a good job of explaining that. Yeah, hopeful. So, and I think that'll help with when I go through the algorithm. But so first we want to modify our tractable optimizations by adding a trust region on the pi theta c o optimization. So this trust region is, keep this KL regularization below some epsilon, right? And you pick the epsilon. And this is good for smooth distributions because it has to be integrable. The expert policy is a Gaussian distribution. So remember I said we spit out a Gaussian distribution of motion primitives. And so this works. However, yeah, I'm just highlighting that term, the KL, the trust region update. So for the other optimization for the context space, the curriculum, this doesn't work because we're not smooth. So that phi c can change, its output can change dramatically, especially in the initial phases of training, right? So you might get derivatives to blow up, slopes of that space to blow up. So we can't use the trust region in that case. And so instead we use a PPO. Let me show you that. So this is all calculable. This is closed form. We can calculate this. This is pi old from the last one. We just ran through the training and calculated these, but this one ends up being a PPO clipping. So this is just like proximal policy, where we have some probability of that context for O times some scoring. And then if that's above, we want it around 1. So if it's above 1 minus epsilon or 1 plus epsilon, we clip it. So this is a figure of showing a bunch of the contexts, so experts, sorry. So each color, I think this had 15, I don't know actually if it said how many experts, but anyway, there's a bunch of experts. Each color is an expert in the state space. So this is the 5-link reacher. So it's hard to see, but this has 5 joints. It's 5-segment line. It's got to go to a goal. And so you can see if it was totally straight, it would map out a circle. So that's the context space. And each expert is specializing in a specific context space for the goals it gets. Figure B is showing overlap. So this is that entropy term that promotes diversity. So red means there's like around 7 experts overlapping in this dark red region. And they found that these regions of high overlap correlate to goals that are very close to the initial position of the reacher. So these are theoretically very easy to learn locations. So a lot of experts learn them before their curriculum updates to more difficult tasks. So here's a sampling of the motion primitive. So you have several trajectories that the reacher can go to different goals. And this is just showing the actual context space of the reacher. So sort of showing the high level view of like multiple experts. They overlap a little bit, but they also specialize. So here's the algorithm.
So Jacob, maybe, so which one of the two, the diversity or specialization, which one emerges and which one you reward at the level of the loss function?
Well, you're rewarding both of them. The specialization, I would say, emerges, I suppose, but
I mean, there was, yeah, so there was the term that you said, some term you said that was, okay,
yes.
so you're saying this term is actually rewarding the specialization, and then the diversity just comes from the explorations because of the entropy term.
You reward entropy, right? You reward entropy
Okay.
in the context space and in the motion primitives. So you want diverse motion primitives and you want diverse contexts, right? So this is contributing to the overlap, and this is contributing to the specialization.
Are they just killing each other, or I mean,
yeah, they're fighting these terms. That's what I was saying earlier. These terms are fighting each other, right? A specialized expert is not a diverse one, right? And a diverse expert is not a specialized one. So, but so that's why I was saying you have to choose alpha and beta to allow balance in those. So there's an art to that, I'm sure. I haven't actually implemented it, but
okay.
So let's see. Oh, so the algorithm. We're looking good on time. Sweet. Maybe I'm going too fast. So pi theta c. So this is the training algorithm. So we're looking for the policy given a context. What's our motion primitive? How do we want to actuate our device? So for k equals 1 to n do. So n being how many episodes do you want to train over? So we sample the context. So if you have the environment, you can just reset the environment without any interaction, and you get a context. So the environments they're using are built to do that. So you just reset the environment as many times as you want to get a C vector. So however long your C vector needs to be, you just sample the environment that much to get the context. And now this is the experts. So for all the experts, iterate over each expert, find the context. So from these contexts, find the context that that expert is more inclined to use. So that's pi c theta. And remember, that was learned through the energy, the scoring. So that neural network in the energy function scores this C, and pi c theta uses those to spit out some CT. These are training contexts. So given the training contexts, find the motion primitives. Given those motion primitives, find the reward that your modeler assigned. And then using that reward, optimize the gradients in each of those. And then that's it. So keep doing that. And so once you've trained this, then you want to use it to actually move a box or hit a tennis ball or whatever. So what you do is you sample the context space, you put those into your learned gating policy that chooses the expert. Given an expert, you now output a motion primitive and you get a reward. So that's the use of this now that it's trained. So yeah, this is the pictorial representation of that. To me, this is a lot more confusing than this, but essentially you have the inference and the training phase. Blue is inference and training is orange. So here's that. You sample contexts. Here's the neural network that assigns scores to those contexts. That allows you to choose a training context. You put that into the expert. This is O. This is the expert. That spits out a motion primitive. You then see how well that motion primitive did and assign a reward based on that. And then optimize. So results. So SVSL, I forget the exact expansion of this acronym, but this is essentially an MOE baseline that was designed to be a baseline. It's linear expert models and Gaussian context spaces. BBRL is black box reinforcement learning. So it's not mixture of expert, it's just taking a giant network, and you still might be able to get diversity in that network. It's just larger and more unwieldy. And so it's just comparing those, and V2, V3, so this is ablation. So they actually killed the specialization term and increased the diversity term in those optimization problems. So this decreases as you go from nothing to 2 to 3. You're increasing diversity and decreasing specialization. So they're claiming that you know, the D-skill that they're calling it, diverse skill, they're saying you need specialization to make it awesome. So that's, and over here, PPO, a lot of these models are dealing with very sparse reward. If you know about PPO, it's taking a, it's finding an action for every time step, a Markov, given a state. What action do you want to take for that state, and rewarding each state. But if your reward only happens at the end of an episode, you're not going to learn very well, because you can see this IQM is very wide here, and also it doesn't learn very well because the reward's so sparse. You can't find good actions if you don't have rewards for them. Whereas SEPs works a lot better for that, because you're actually finding a motion primitive, right? A trajectory. So you wait till the end of the episode to spit out an entire trajectory, whereas PPO is trying to find individual actions along the trajectory. But you don't get a reward till you're finished the trajectory. So this is why SEPs works better. So for a variety of environments, I forget what all of these are, but they're claiming that you know, if this is matching, so Lindy skill, so they found that SVSL wasn't a great comparison, so they actually just linearized their method with linear models rather than nonlinear expert models. And we discussed this. I think there was a mixture experts paper a couple weeks ago, and there was a lot of discussion on like, why does highly nonlinear expert models, why are they better? And so I like to think of this as, so in optics, there's something called the Keir effect, where you have this nonlinear self-focusing based on the intensity. So if your light is intense, it focuses more because of the index of refraction, and it gets more intense, so then it focuses more, it gets more intense, focuses more. And they've used modulation instabilities to get signal from noise. So you have some image in a lot of noise, and the image is signal, the noise. The image is slightly more intense than the noise, usually in the aggregate, so it self-focuses, and it's because of the high nonlinearity. And here as well, that's how I like to think of it anyway. So you have this signal that's going into a highly nonlinear model that helps self-focus that signal, and at the expense of the noise. So that's how I think of using highly nonlinear models for each expert. And so anyway, in the red, they use linear models in this whole setup, and they find it in a lot of cases. But for the environments where they're matching BBRL, they're suggesting that those environments don't necessarily need a lot of diverse skill. I'm not sure how I feel about that, because I'm not too well versed in BBRL, but I imagine if your model's big enough, you can still learn diversity. But you know, I don't. It's just harder, or takes more compute, I would think. But I mean, I don't know. At least that's my understanding, and I would love to discuss that more if people want to. But so yeah, PPO again, sparse rewards, not learning a trajectory, just learning actions. So here they're showing how diverse the skill sets can be. So this is, I think the red is the goal. They're trying to move this box over to red, and they're oh no, red's an obstacle. They've got to move a box to the goal around red, and they're finding lots of ways to do it. And that's the diverse learning and specialization of each expert, right, doing that. And again, they're showing that here. So there's what this one has, I think 5 or 7 degrees of freedom robotic arm with a paddle. And they're trying to hit the same point on the opposite side of the table. And it learns several different strokes to do that. So it has multiple experts that specialize in a different stroke, and they can hit the ball. And that's all I got. I don't have a question slide, but let's talk.
All right, so I have two groups of questions. So one's about linear, non-linear. So my understanding of why non-linearity is important is because if you have a linear transformation, you have many linear transformation one after another, and you can all collapse it to one, right? The product of matrices will just give you one matrix. The sum of matrices will just give you a matrix. So there is not, you're not going to get something without non-linearity. And so once you add non-linearity, now you're in business. It's now composition of transformation is no longer can be reduced to just one. So that's just my take on. But I don't know. Maybe in context of this mixture of experts, there is something more to this. Actually, that's kind of related to the second question I have, because the main point here that I'd like to better understand is diversity versus specialization, right? So now let's say I take a problem, some learning task, and I try to make it. As I'm learning task, and I make it more and more complex, but I do not increase the resources. Now, would it now make sense for me to use this mixture of experts, and each of them would be specializing in one particular tasks, as opposed all of them having a specialization in all tasks? So my understanding was the mixture of experts is exactly for that situation. You have constrained resources, very difficult task, and then you just have each expert learn something, and then there are overlaps. There is some diversity, which we call, but it's not a feature; it's a bug. You would rather not have that. You would rather have each of them learning something separately. And since you are showing this formula, in terms of this formula, what it would mean is that if they would add a coefficient to the exponent, which is the right way of writing the distribution, the canonical distribution, they should be like minus beta phi 0 of C. So now if you take this beta and make it very, very large, then it would mean the temperature is very small, and then there is really one expert for each context. Or few, one is an extreme point. So that I would think that this is the limit where this specialization would be more useful. I'll just say it once again. Very difficult computational task or learning task, and a restricted number of resources. But I don't know if do they have like a plot of exploring this? When is it that the diversity needed, and when is it that the specialization is needed, as on this two-dimensional plot of the complexity of the learning task and the number, the resources that you're taking. Yeah. So here you're showing the B, right? So in B, like red, I would say those are bad regions because there's too many experts there.
I wouldn't say bad, because you don't want. I mean, there might be.
They're trivial because every single one kind of learned it already. There is not
totally, but you do want some overlap, right? Because you don't want to miss you don't want to miss context space, and B, you don't want just this discontinuity between this exact
1, 2,
fitting.
3.
Totally.
1, 2, 3, whatever. Small number. And that's
totally.
what would correspond if you take this beta parameter, which was missing in that formula, but should be there, to infinity. And or when you're saying that there is only one dominant energy to each context for each expert. So I still think that those red regions are just trivial to learn, and so every expert.
And they mention that these, like you can see, they make a pattern. And they're almost always near where this reacher arm starts. So
right, exactly. So they have too much training data there.
Exactly. Yeah.
Yeah, so that's not so it's not kind of you're abusing resources. You are using two different experts to learn the same trivial
Yep.
task.
Yep.
Uh, but my question like would be more in the limit where you have constrained resources, right? The computational task becomes more and more difficult, and then you don't want to have those overlaps. So you really want experts to learn something, and then I would think that's where you would see this, strong preference towards specialization would emerge. And the diversity would just be a bad thing, right?
Right.
Yeah.
Yeah,
About
and well, it's important. It's also important to note that the context is being learned. So the context space, right, is, I mean, that's
well,
how,
not the context learned, but what is learned at which expert is gonna
yeah,
be responsible for a given context. So this is, and it's of course this is like gating function, right? It will tell you which expert should you be using for a given, you
but
know.
this automatically ratchets up the curriculum as as the expert learns, right?
No,
So,
this thing is back propagated, and I understand that this function needs to be learned. If the expert shoot out some bad decision, then it will get, punished for that, and next time its energy will be smaller. Again, to call its
right.
energy, you really need a minus sign and a beta there. Otherwise, it's not energy; it's negative of the energy times beta.
Yeah, I know.
So
And
it's not energy, but I get
right.
it. I mean, I
Yeah.
understand where this comes from,
And
and
I
I would
honestly
say,
think that's a mistake of the paper, but I mean, it's convention, right? If as long as you keep it the same, the
well,
the
I would think that
object.
this parameter beta that is missing there should be added. This would control their specialization versus diversity. So it would be added to this expression. Um, well,
So
I don't know if it's here because
I
this
mean,
is just a loss function, but in the actual weighting, it may translate to some parameter here.
but
Okay.
you're weighting that exploration here.
Yeah.
So by rewarding entropy in this scoring, you're
That's an indirect way of doing that. Yeah, you can
right.
do that. It's in the indirect way of, yeah. So certainly, you can instead think about. Okay, so where does this parameter comes from? Beta that I keep talking about. It comes as a Lagrange multiplier in the entropy maximization problem with a fixed energy. So you take, I want to solve a problem of a fixed average energy subject to maximum entropy principle. And then you set up your variational problem. You write some entropy plus beta times energy phi zero here minus your expected energy, the energy that you want to have. You do variational, and then this beta parameter appears there. I just don't see it's here, and that's why. But you may be right. This will just translate to some term that appears in that variational principle. But this beta is a Lagrange multiplier that is multiplying the energy usually, and there it is multiplying the entropy. So maybe it is like its relation is like 1 over beta
So
there is
y-
1 over beta, which should be here, something like that. So,
so I'm not familiar. So you're saying there should be a beta in the
well,
exponent or out?
if you want to talk phi zero, if you want to call it energy,
Sure, sure.
yeah. So then you should have exponent minus beta times the energy, and that's your canonical distribution. And then the smallest energy would correspond to the largest probability. So if phi zero is very small, then this is corresponds to the having a large probability of being in that state, and then all this is meaningless unless you specify this parameter beta, because beta will tell you, well, how much do you care about energy being a little bit smaller or a little bit larger? and that is
Yeah,
the
and
parameter beta.
I'm still saying that's taken care of here.
Yeah, it's
but-
probably this beta, but since this is entropy, and I bet it is not beta, but 1 over beta. Yeah, so I think you're right. I think you're right. This is if H is H entropy, is it a?
Yes, yeah. So this
Okay.
is if I mean, so if you're allowing sorry. So if you have a low or high score here, if pi CO is high or low, right? You're taking the Shannon entropy. This is exactly that. It's the Shannon entropy of pi CO. So you know, if
Yeah,
it's
so the usual convention is to write here, to remove beta from here and then put beta next
put
to
it
the
in
LC. So like divide everything by beta here.
Sure, okay.
And then there will be beta to the -1, which is the right term, and it would correspond to the energy. But again, I mean,
it's the right term or the other way. That's
yeah. Well, if you want to call the other thing energy, if you want to call
sure,
it,
totally. Yeah,
I'm
sure.
just saying that if you want to set your variational principle correctly and call that energy, and then inverse beta will be temperature and in the canonical distribution. Okay, perfect. I think I understood something, so that's
yeah.
so
Cool. Yeah, and I you know yeah. I hope I explained it well. This was a tough paper for me. So it was, yeah.
Thanks. Yeah. Any other questions, comments? Okay. Well, thank you, Jacob. Great talk, and I'll see everyone next week. Thanks a lot. Thanks for coming.
Awesome. Thanks, everyone.
Thanks.
Bye.
Bye-bye.